Hi everyone, Mr. Lee here. In this video, I'm going to go over Newton's 3 laws of motion. These 3 laws are really cool. They help describe how things move here on Earth. It helps us describe how things move on the moon. It helps us how things move like when you're halfway across the galaxy on a distant planet. These laws really help describe how things move throughout our known universe. Super cool things. So let's dive into it. The first law is the law of inertia. Okay, it says an object in motion will stay in motion, an object at rest will stay at rest. Which just, if you really think about it in terms of equations, that means that an object with a velocity will have constant velocity. And let me show you why this is important. So we know that if you have a constant velocity, that must mean that your initial velocity and your final velocity, they're the same. And if we know that acceleration is a change in velocity over the change in time, and the change in velocity is final velocity minus initial velocity over the change in time. And if these two numbers are the same, and we were to subtract them from each other, we will get 0 over the change in time, which states that if your initial and your final velocity, they are the same, that means your acceleration is 0 meters per second squared, which is the law of inertia. Okay. As long as there is nothing affecting the motion of an object, it'll continue doing its thing. Okay? All right, so that big idea really comes into play here with the second law. Now, the second law is the law where we have the equation itself, and I have that out in front of you. So the second law states, an object that experiences an outside unbalanced force will accelerate. Okay, and much like the definitions in physics, the equation and the definition, they go hand in hand. So here we have the definition and the equation right here. We say that if a object, which is the mass, if the object accelerates, okay, we look at the object and it's like, that object is accelerating, that must mean that there is a outside unbalanced force. Okay, and we're going to go into why that outside is important. The word unbalanced simply means that when you add up all the forces, by the way, this Greek letter here, okay, that's sigma, that means total, or the sum, or the summation. So if you were to add up all the forces, you will get a number. And when we are talking about unbalanced forces, that means that when you add up all the forces, it is it's a number that does not equal 0. Okay, so as long as the forces don't add up to 0, that means you have an outside force. So if we have a outside unbalanced force, the object will accelerate. Okay, objects are known as with the variable m for mass, and that's in kilograms. Acceleration, we know, meters per second squared, or meters per second, and force, we have capital N for newtons. Now, let me do a quick little problem with you to show you the big difference between the 3, because oftentimes in our everyday language, which is sometimes different than our physics language, it gets a little bit confusing. So I'll use myself as an example. I, Mr. Lee, have a mass of right around 75 kilograms. Okay, and my mass is what I'm made up of. Right? So if I were to go to the moon, I will be myself, right? I wouldn't change. My mass would not change. The acceleration due to gravity, so this is how hard the Earth is accelerating me, my object, or myself, is negative 9.8 meters per second squared. Now, just for the sake of math, I'm going to say that's right around negative 10 meters per second squared. Okay? So if I wanted to know the force that the Earth is exerting on me, so the force that the Earth, gravity, is exerting on me, I would multiply the two together like so. And I would get 75 times negative 10, which is equal to negative 750 newtons. And that negative simply means that the Earth is always pulling me down. Gravity is always pulling me down. All right? All right. So if I were to get myself and I were to go to the moon, the acceleration of gravity on the moon is different. It's not negative 9.8, right? It's right around negative 1.6 meters per second squared. And for the sake of me doing my math, I'll say that's like negative 1.5 meters per second squared, right? So if I were to take my body, my mass, and I were to go to the moon, and if I were to stand on a scale that tells me my weight in newtons, I would use the same formula, F is equal to ma. My mass does not change. However, the acceleration due to gravity does. And that's negative 1.5. And that would give me roughly 112.5 newtons. Okay, so my weight on the moon is significantly less than my weight here on Earth. So I will feel so much lighter. Now, just as a heads up, here in the States, we describe the Newton or the force in pounds. All right. However, we don't use pounds, we use newtons to describe the weight or the force, right? Because F of G can also be known as the weight. So oftentimes kilograms and pounds, they're used interchangeably, but they're not. They're really different for us here in physics. Okay, now let's go into the third law. This is where things get really cool. So the third law states, whenever one body exerts a force on a second body, the first body experiences a force that is equal in magnitude and opposite in direction to the force that exerts it. I rewrote this to say, if object A has a force exerted on it by object B, object A will exert a force back on object B with equal magnitude but in the opposite direction. And the best way to approach this is with a couple of examples. So here we have a person pushing on a wall, and you could try this if you have a wall near you, or instead of a wall if you push down on a desk. Okay, so if a person pushes on the wall, and let's say the person pushes on the wall with 700 newtons, the wall will feel 700 newtons of force to the left. Okay, and you could try this if you push on the wall. If you push on the wall, like let's say you're pushing on the wall to the left, if you really focus on feeling the sensations in your hand, you'll notice that you don't feel a push going to the left. You feel what the wall is doing to your hand, which is a force back in the rightward direction. So if you have a desk and you're pushing down on your desk, if you focus really hard on what your hand feels, you don't feel a force pushing your hand down, because that would be something like this, right? If I were to push my hand down, I feel this down. You feel the surface of the desk pushing back up on you, which is the opposite direction. So in this case here, the wall experienced 700 newtons of force to the left. And so what does this guy feel? This person feel? This person feels that the wall is pushing them back to the right with 700 newtons of force. Equal, but opposite. Okay, so let's take a look here on you sitting in a chair. So if we have a person sitting on a chair, okay, the force that's being exerted on the chair is this person's weight. So the chair feels a force of, let's say the weight is 700 newtons. Okay, the chair, it's like it feels the weight of 700 newtons pushing on it. So what does the person feel? Well, if you're sitting down, you could experience this yourself, right? What do you feel? You must be feeling the chair pushing back up on you. That's what's holding you up. That's why you're not crashing through the chair. The chair is pushing right back with the same amount of force. Okay? And because these two are equal, you are able to sit on a chair. If they weren't equal, you would just crash right through. Okay? All right, so let's do the next one. Let's do a duck swimming or a person swimming. Now, if you notice here, my scuba diver, I'm not really good with arms, so I decided not to give this person any arms. But here we have a duck. The duck, when they're swimming, when their feet are paddling, okay, the duck's feet push the water backwards. Now, when the duck pushes the water backwards, according to Newton's laws, what is the water doing? Yeah, you guessed it right. The water is pushing the duck forward. And this is important because remember how I'm using my words. The water pushes the duck forward. The water pushes, which is F, the duck, which is the mass. And so when the water pushes the duck forward, we can see that the duck will accelerate. And this is true, like for example, if the duck was just like floating there, not moving, and then the duck like kicks the water, okay, you're going from rest to a state of motion, therefore you accelerate, right? And so like that's what allows ducks to swim. And it's the same idea for you swimming yourself. For the scuba diver is going to kick with their feet, and that kicking motion, they are pushing the water behind them. And so because they're pushing the water behind them, what's the water going to do? You guessed it, the water will push the scuba diver forward with an equal amount of force. And so that's what allows you to swim. All right, now the final one is one of my favorite ones. It's really a head scratcher. So if I am walking, all right, so a couple of things. Imagine yourself walking. You're walking forward. Now when you walk forward, there's two parts I want you to focus on. When you walk forward, your walking foot is moving behind you. Okay, your moving foot is moving behind you, yet your torso moves forward. Okay, so keep that in mind. Your torso is what's moving forward, but the foot that is on the ground is moving behind you. All right, so if I take a look here, I have my foot, and the foot is pushing down on the earth. Let's say with, I don't know, 100 newtons of force. And so the earth will push back upwards with 100 newtons of force. And that N means the normal force, because this is a surface, right? The surface, or the normal force is a surface force, and it's perpendicular to the surface. However, remember, this person is moving to the left. So if the person is moving to the left, yet this normal force is pushing upwards, these two are not the same direction. They're not the same. So that means that the surface, or the normal force, pushing upwards is not what causes the person to move to the left. Okay? All right, so let's get that out of the way. And so what is causing the person to move forward? Now, I want you to remember this. When you're walking, the foot moves behind you. Okay? So that is the motion. So in the previous video, I talked about friction and how friction always goes against the motion. So the force of friction, if your foot itself is moving behind you, then that must mean that the force of friction, which goes against the motion of the foot, is what is pushing the foot forward. Okay, and the foot is attached to your body, and so when you're walking, the force of friction is allowing for your body to move forward. And that's because the foot is exerting a force on the surface, which pushes the surface backwards. So simply put, whenever you're walking, you're moving the earth behind you in order for you to walk forward. I'm going to say it one more time. When you're walking, okay, you're pushing the earth behind you so that you can walk forward. So in a way, when you're walking forward, it's because that the earth and the friction between the foot and the earth itself is pushing you forward. Whoa! This is also true whenever you jump. Okay, whenever you jump, what you're doing is you're actually pushing the ground down. Okay, you're pushing the ground down. And in order for you to push the ground down, what's the ground going to do? The ground is going to push you up. And because the earth has a much larger mass, it doesn't look like the earth moves, but you move because that's how you're able to jump. Okay, so the very last thing I want to end this video with is a quick little experiment. I've been saying you can't exert a force on yourself. Something else must push you, right? An outside force must be able to push you. So two things. If you're sitting there in your chair, get your hand and push yourself on your chest. And no matter how hard you push on your chest, right, unless you're being dramatic, you're like, whoa, and you fly backwards, your torso doesn't move. However, someone else pushes you on your chest, you'll move backwards, right? And the next one, if you wear your shoes, right, with shoelaces, okay, if someone else lifts you up by your shoelaces, you're going to move upwards. But if you grab your shoelaces and you pull yourself upwards, unless you're being dramatic, you're like, oh, look at me, I'm pulling myself up, you're not going to move. Because you can't exert a force on yourself. Something else must exert a force on yourself. Anyways, this was Mr. Lee with Newton's laws of motion. Really cool things. Affects the entire universe as we know it. And until next time, I'll see you later. Bye-bye.